Okay, so yesterday we talked about GNSS measurements and different sources of error in the GNSS measurements. And we also briefly talked about PVT, position, velocity and time, how we can find the PVT from the GNSS measurements. Uh, in this context, also note that um, the pseudo-range measurement is derived from the code. Okay, using the pseudo-random code, we can obtain the pseudo-range measurement. Similarly, using carrier also, we can find the range measurement that is much more precise than pseudo-range. And you should also note that the code and carrier travel at different speeds in the ionosphere. Okay, we'll talk more about it later. But you should note that code and carrier travel at different speeds uh, uh, in the atmosphere. Code travels slower than the speed of light, at a speed slower than the speed of light in a vacuum, whereas carrier travels faster than light in a vacuum. We'll briefly discuss why this happens, but we'll not go into details of radio physics. We'll start with some equations from radio physics, and then we'll see that code and carrier travel at different speeds. And since carrier travels faster than light, the ionospheric error that we get uh, when we derive the measurement, range measurement using the carrier is negative. Okay, whereas for code it is positive. Now, as per Einstein's theory of relativity, nothing can travel faster than light in a vacuum. Okay, so an electromagnetic wave can travel faster than light in a medium, and the propagation of the carrier in the ionosphere is an example of that. This is not in violation of the theory of relativity, because theory of relativity talks about the propagation speed in a vacuum, whereas in a medium, an electromagnetic wave can travel faster than light. Okay. So today we are going to first discuss the sky plot. So it tells us the distribution of the satellites. In the sky, as seen by the user. Okay, and here we plot the satellites as a function of two angles, azimuth and elevation. So let's define these two angles. We already defined elevation. We also talked about azimuth, but with a different name called bearing. In case of GNSS, we do not use the term bearing, rather we use azimuth. So let's again define these two angles in the context of GNSS. So here we have the user. User can be on the surface of the earth, or she can be at some altitude from the surface of the earth. So this is the user, and this is the satellite. So we join the user and the satellite, and the line is called LOS, line of sight. Right. Next, what we do is we pass a plane through the user but making the plane tangential to the earth surface. So if we shift the plane from the user to the surface of the earth at this point, which is the projection of the user on the surface of the earth, we'll see that the plane is tangential to the earth's surface. Okay, and then elevation is the angle that the line of sight to the satellite makes with this plane. Okay. Now this is the projection. This white line on the plane is the projection of the line of sight on that plane, right? Now let's see this line, the projection of the line of sight on the plane. So now we are seeing the plane from top. This is where the user is, and let's say this is the line, which is the projection of the line of sight on that plane. And this, let's say this is the direction of local north at the user. So this angle, which is calculated clockwise from north. So azimuth is positive when we calculate it clockwise from north and negative anti-clockwise. So this angle is azimuth. So psi is azimuth and theta is elevation. Okay. Now theta can be between plus minus 90 degrees. Okay. So it is 90 degrees. Theta is 90 degrees when the satellite is overhead, just above the user, and theta is 0 when the satellite is on the horizon. So this direction is called zenith. Okay, satellite is overhead when theta is 90 degrees, and this one is called horizon. When the satellite is on the horizon, then theta is 0. When satellite is at the zenith, theta is 90 degrees. So this is when the satellite is above the user. Similarly, it can be go below the user, especially when the user is at a high altitude. Satellites can be below the user until it is blocked by the Earth's curvature, Earth's surface. Okay. So the range of theta is plus minus 90 degrees. Whereas azimuth can be from 0 to 360 degrees. So if we keep calculating it clockwise from north, we get 0 to 360 degrees, or we can have plus minus 180 degrees. So in that case, in this direction we have 0 to plus 180 degree, and then on the left side we have 0 to minus 180 degrees. So either we can say 0 to 360 degrees or within plus minus 180 degrees. Generally we use 0 to 360 degrees. Okay, so now let's see how we can represent the satellites as a function of azimuth and elevation pictorially. So the sky plot, when you use the software, you will find that you get a plot like this. Okay, here we have a number of concentric circles. And then the center is where the user is. Okay, so user is at the center. And that represents zenith, 90 degrees elevation. Okay, all these different circles represent different elevation angles. So here we have 90 degrees. Then as we increase the radius, we actually reduce the elevation angle. So on the outside, you will see that they have given a dashed line, dashed circle. So any satellite that is below this elevation angle, so this corresponds to some elevation angle. So any satellite that is below this elevation angle is not considered by the user receiver, user requirement. Okay, so this threshold elevation angle is called the mask angle. So any satellite below the mask angle is not considered for positioning or PBT estimation. Generally, it is seen that low elevation satellites are more prone to multipath, so they may get reflected many times. They are more prone to multipath and then reach the receiver. If they get reflected and then reach the receiver, they are actually corrupted. So we are not interested. Generally, we are not interested in multipath, but there are some applications where we can get useful information about the uh, the ground or the structure from which it gets reflected. So, for that application, multipath is important, but we generally do not consider multipath. So low elevation satellites are more prone to multipath, which is number one. Number two, when the satellites are near the horizon, they travel longer distance to the atmosphere, and there is a higher chance that they get more atmospheric errors. Okay, so generally we do not consider low elevation satellite, but again it depends on application. But the usual practice is not to consider satellites uh, below some threshold. And threshold can be determined by the user. If the user wants to consider all the satellites, he will pick a negative threshold. He can select a negative mask angle, zero mask angle, but typical value is 5 degrees. Okay, typically we consider 5 degrees mask angle, and any satellite with elevation below 5 degrees is not considered for estimating the PVT. Okay, then you will also see some radial lines. Okay, like this you will also see a number of radial lines. This line corresponds to 0 degree azimuth. Okay, then we go clockwise and increase the azimuth 30 degree, 60 degree, 90 degree, and so on. So this way we go, usually we write 0 to 360 degree clockwise, or one can write 0 to plus 180 degree clockwise, and then 0 to minus 180 degree anti-clockwise. Okay. So the radial lines represent azimuth and the concentric circles represent elevation. Then when you generate this sky plot, you will see many satellites, and they, since the phone can receive signals, smartphones can receive signals from the four global constellations: GPS, Galileo, GLONASS, and Beidou. So you will get to see all the different satellites from different constellations, and they use different colors or markers to distinguish between satellites of different constellations. Okay, so you will see satellites like these. So everywhere you will see satellites, depending on the geometry again. So where you are collecting the data, at what time of day you are collecting the data. So depending on all this, you will see different distributions of satellites from different constellations. Okay, any question? Okay. Next, I'll quickly talk about C over N naught. It's called carrier power to noise, power density issue. Now, if you do not understand what noise, power density is, actually it is power spectral density, don't worry about this. We'll define both power, signal power and noise power spectral density when we talk about filtering and estimation. But at this point, we will not go into detail. We'll just note that C over N naught, carrier power to noise power density ratio, is an important metric used to quantify signal reception environments or quality of signals. It is expressed in logarithmic scale. And the unit is dB hertz. Since the scale is logarithmic, we have dB and then hertz comes. That will be clear to you when we talk about the definition of the power spectral density. Okay. Now I'll give you representative figures of C over N naught, because when you process signals using the software, you will see a plot, C over N naught plot, C by N naught or C over N naught plot for different satellites. And this will tell you the quality of signals that you get from the individual satellites. Generally in open sky environment, open sky means you are receiving signal outdoors. Okay, there is a clear visibility of the sky. No obstruction, signals do not get obstructed. You get direct line of sight signals from the satellite. Then the C over N naught will be in the range of typically 40 to 50 dB hertz. So generally, if you see 35 to 50, you will consider it a good signal reception environment. Okay, so this is good. Then 30 to 35 is okay. 30 to 34. 30 to 35 is okay, not bad. Below 30, generally we consider low signal environments, okay. Some people say below 25. Depends on receiver design, how sensitive the receiver is. If it is designed to receive low signals, weak signals, low C over N naught signals or weak signals, then 30 is not so bad. But let's say below 30, we have low signal or low C over N naught signals. Okay, typically in indoor environments, the C over N naught will be below 25. Okay. Depending on where you are receiving the signals, it can be even below 20. Okay, so you can get below 20 also. Now, a conventional receiver generally do not receive signals if C over N naught is below 20, okay, below 20 or below 19. Now, if you want to receive signals at very low C over N naught below 19, then you need to go for sophisticated designs or advanced designs. For that, different designs are available. But generally, a conventional receiver do not receive signals below 19. Okay, so when you use your smartphones and plot C over N naught, you will get an idea. To start with, you should receive first collect data outdoors. Okay, that will give you an idea about C over N naught you are getting. Then, if you are interested, you can also collect data indoors. Okay, but I would recommend that you first collect data outdoors, open sky environment, clear visibility of the sky, and then do everything, all the analysis. After that, if you are interested in collecting more data and see how things are, you can do the data collection inside a building, indoor environment. When COR drops, we also have less accuracy. Okay, so we cannot trust position estimation when COR drops. Depending on receiver design, 25 up to 25 is okay. But below 25, again, how the receiver has been designed. I don't think the smartphones will have high accuracy, sophisticated design. So conventional design only, I think, is used so far, at least in commercially available smartphones. So up to 25, we can somewhat trust the position estimation, but below that, will not be able to. So when you so basically you should also collect data for a stationary position, and then since data will be collected over the period of time, and then at each time instant, every second, generally every second you will get the position estimation, and you, if you stand in a particular place, you will see the spread of the position estimation. So it should, ideally it should give the same position, right? Because truth does not change with time. But you will see that the spread increases as you degrade COR. As the signal quality becomes poor, the spread of the different position estimates over time increases. So that indicates, because you do not know the truth, what your true position is, do not have any other reference. Google Earth gives 2D position for us, as far as my knowledge is concerned. We do not get 3D. The best way to see, without any reference, best way to see whether you are getting good accuracy or not is to collect data over a period of time at a stationary position, and then do UVT estimation for all these time instants and see the spread. Okay. That's about COR. Do you have any other question? I mean, any question on COR? Any clarification you want? Are you following? I hear no response.
Yes,
so are you following? Okay. How about others?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Next, I'll tell you a few things about the clock. So whatever I'll discuss applies to satellite clocks also, but my focus here is basically the user receiver clock. Okay, a clock is actually an oscillator. Later we'll talk more about clock. So for the time being, just note that it is an oscillator. So it oscillates at a particular frequencies. And then we can have an electronic circuits. That measures or keeps track of the number of oscillations. So let's say the advertised frequency advertised or nominal frequency is 1 megahertz. Okay, let's say this is the nominal frequency of the clock, 1 megahertz. This means this clock is supposed to make 10 to the power 6 oscillations in a second. So if we have an electronic circuit that keeps track of the number of oscillations, and when it measures 10 to the power 6 oscillations, it will know that 1 second has elapsed, right? Then it can output 1 second, right? Then when it measures another 10 to the power 6 oscillations, another second has elapsed. So this way, by counting the number of oscillations that the oscillator makes, we can keep track of time. So this is the basic principle, operating principle of a clock. But here the problem is that there is no perfect clock. Okay, that's why I have used this term advertised or nominal frequency. So the nominal frequency of a clock may be 1 hertz, but it can be possible that it is actually making 9 point, let's say, so basically 10 to the power 6 minus 1 oscillations. So let's say F naught is 10 to the power 6 hertz, 1 megahertz, and F is 10 to the power 6 minus 1 hertz. Right, so that will be 99 hertz. So this is the nominal frequency. This is nominal frequency, and this is actual frequency. Okay. Now the accuracy is given by the term relative frequency deviation. Which is F minus F naught by F naught. Okay. And generally we are interested in the magnitude. Okay. So in this case, nominal frequency is 10 to the power 6, actual frequency is 10 to the power 6 minus 1. If we use these values, we'll see that the magnitude is 10 to the power minus 6, magnitude of RFT is 10 to the power minus 6. So you can say that the accuracy of the clock is 10 to the power minus 6. Okay. Now there is another way of saying this. So 10 to the power minus 6 can also be said as 1 part in a million. Now if a clock gives an accuracy of 10 to the power minus 9, one would say 1 part in a billion. So this is a convention that is also followed. So either one can say accuracy is 10 to the power minus 6, or one can say 1 part in a million, 1 part in a billion. So if it is 10 to the power minus 8, then one can say 10 parts in a billion, or 1 part in 10 to the power 8, like that. Okay. So this is another convention. So accuracy is basically a measure of the actual frequency, how close the actual frequency is to the advertised frequency, the desired frequency. But there is one more quantity called stability, which is also very important with, in case of clocks. Okay. What is stability? Stability measures the ability to operate at a particular frequency or desired frequency over a period of time. Now, depending on the duration of time that we consider, we have two types of stability: short-term stability and long-term stability. So, short-term stability is generally measured over a second or few seconds, and then long-term stability, again depending on the duration that the manufacturer considers, it could be over a day, over a few years also. So they in the manufacturer data sheet, they specify the time for long-term stability over 3 years, 5 years. Generally, I have seen they show long-term stability over 3 years or 5 years, like that. Okay. So here we are actually attaching a period of time. The ability of the clock to operate at a particular or at a specified frequency or a particular frequency over a period of time. Because time is important here. So maybe over a second it can give good short-term stability, but over longer duration, it may not be that accurate. So unless we attach the duration of time, our definition is not complete. Okay. Now again, RFD, relative frequency deviation, is used to specify stability. Okay, but it depends. I mean, what duration of time you have considered to determine the RFD, relative frequency deviation, and that will determine whether it is short-term stability or long-term stability. Okay. Now, when you process data, you will get some plot for the clock error also. Okay, and you should pay attention to the unit, how they are expressing the clock error, and let me know what you think about it. Okay. Now you may ask how we can relate frequency error to time error, right? So let's say a clock has an actual frequency f and its nominal frequency is f naught. So frequency error delta f is f minus f naught. So one would be interested in knowing how much time error it incurs, right? So let's say delta t is the time error, over actual time capital T. So we want to relate delta T to frequency error, right? So let's do that quickly. Now, when the clock makes f oscillations, let's say since we have considered capital T, ft oscillations, because its actual frequency is f, not f naught. F naught is the advertised or nominal frequency. So when it makes ft oscillations, that is equivalent to time capital T, right? When it makes one oscillation, the corresponding time is t by ft, and t cancels out. When it makes f naught time t oscillations, the corresponding time is f naught t by f. So this is the number of oscillations, and this is the time, actual time. So when the clock makes f0 times t oscillation, the actual time is this. But however, the electronic circuit, it does not know anything about the actual frequency. It is designed to count the number of oscillations. So when it counts f0 times t oscillations, it will tell that t seconds have elapsed, right? So the nominal time corresponding to this actual time, the nominal time is, or the time reported by the clock is capital T. When the actual time is this, the nominal time or the reported time is capital T. So what is the time error? Delta T is equal to F naught by F minus 1 times T, and that we can write as minus delta F by F times T, right? And then if we take capital T on the left side, we can have write small t by T is equal to minus delta F by F. Now, what is the significance of this negative sign? Let's say the actual frequency is greater than f naught. What happens to the actual time? Is it greater or less than the reported time? If the actual frequency is greater than the nominal frequency, meaning the clock is running fast, what happens to the actual time compared to the nominal time? Is it greater or less? Hmm?
Ma'am, less than. Actual
How about
time is
others?
less.
Yes, actual time is less. How about others? Are you following? How about others?
Yes, ma'am.
Yes,
Lesser.
ma'am.
The
Less.
Actual time is when the actual frequency is more, the actual time is less. Okay, so they are actually, they have some sort of an inverse relationship. When actual frequency is more than the nominal frequency, the actual time is less than the reported time. When the actual frequency is less than the nominal frequency, actual time is more than the reported time. That's why we have this negative sign here. Okay, so this tells us how the number of oscillations are translates to time error, right? Now let's say for a receiver clock at some time instant t naught, the error is delta t. Okay, and we are actually interested in finding delta t at some other time instant t1. So this is the delta t at t1 is equal to delta t at t naught plus delta t dot times t1 minus t naught, right? So this one, the delta t at t naught or t1, they are actually called clock bias or clock offset. Okay, and this delta t dot is called clock drift. Yesterday we discussed how these two terms appear in the measurements, GNSS measurements. In pseudo range we have clock bias or clock offset. In pseudo range rate we have delta t dot. Okay, so using both pseudo-range and pseudo-range rate measurements, we can determine these two quantities, clock bias or clock offset and clock drift. Okay, I think that's it about the GNSS overview. Do you have any question? So with this introduction, you will be able to start the project. So the first thing that you have to do is to visit that website and read through it, see all the instructions. You will probably find some articles also, magazine articles. Read them, and you should install the app first and see whether your phone supports raw data collection. So that is important. If you cannot collect raw data with your phone, then you need to manage a phone with which you will be able to. If none of you can manage, then we cannot complete the rest of the project. Generally, that does not happen. Even in 2019, people could get hold of phones, but they were in campus. Last year also they could, although classes were online. So see if you can manage a phone. In case your phone does not support, you can manage a phone that can collect raw data. So do not keep it for the last moment. As I told you earlier, you should start very night. Okay. So that's all about GNSS for the time being. Okay. Next we'll talk about different navigation coordinate frames. We know that with the help of our navigation system, we can get different navigation solutions such as position, velocity, linear velocity, angular velocity, acceleration, linear acceleration or angular acceleration, and altitude. Now, all of these quantities are determined with respect to some reference coordinate frame, right? And almost all of them are vector quantities. So vector quantities means we need another coordinate frame to represent the components, right? So navigation is basically a multi-coordinate frame problem. Okay. Here we generally consider an orthogonal coordinate frame. An orthogonal frame has origin and 3 axes, orthogonal axes. It has 6 degrees of freedom, so we want to know the position of the origin and the orientation of the axis, 3 axes. So it has 6 degrees of freedom, and we generally consider right-handed coordinate frames. Okay. So how do you define a right-handed coordinate frame? We extend the thumb of our right hand up and then curl the other fingers such that the direction is from x to y axis. So and then the direction of the thumb will be along the positive z axis. So if you are not sure whether whether a coordinate frame is right-handed or left-handed, you should do this. And then find out whether the direction of the thumb will tell you whether it is a right-handed or left-handed frame. As per convention, we consider right-handed coordinate frame. Okay, so right-handed orthogonal coordinate frames are considered for navigation purposes. In this class, we are going to define 4 right-handed orthogonal coordinate frames. Okay. The first one that we will consider is called the Earth-centered inertial frame. An inertial frame is one which does not rotate or accelerate with respect to the rest of the universe. Now, it's difficult to find a truly inertial frame. If we can define a frame with the help of celestial bodies, distant stars, we can find a close approximation to true inertial frame. There is an international body called International Earth Rotation and Reference System Service (IERS) based in uh, uh, Paris. Okay, so they are responsible for defining all the reference frames and standards. So they used celestial measurements and defined uh, uh, a frame with the help of distant stars that can be considered almost in an inertial frame. But such a frame is not useful when we are interested in terrestrial navigation, in earthbound navigation. Okay, so for terrestrial navigation, we define an Earth-centered inertial frame, whose origin is at the Earth center. And tomorrow you will see that the Earth's surface is modeled as an ellipsoid, not a sphere. And the center of the frame is placed at the center of the ellipsoid. Now, since the Earth goes around the Sun, this is not a truly inertial frame, but it serves its purpose for terrestrial motion. So, although its origin is at the Earth center, its axes do not rotate with the Earth. Okay? In that sense, it is inertial. So, the origin is at the center of the ellipsoid, and the z-axis points along Earth's spin axis from the center to the North Pole, and the x and y axis are in the equatorial plane. They are fixed, they do not rotate with the Earth. But this does not uniquely define the frame. So we need to adopt some conventions to uniquely define the frame. The first convention is relatively easy. On the next slide, we are going to define an Earth fixed frame whose origin is again at the center of the ellipsoid, but the axes are attached to the Earth. So as the Earth rotates about its spin axis, the coordinate frame also rotates with the Earth. That's why it's called Earth fixed frame. So at the start of navigation, when t is equal to 0, we align the, as per convention 1, we align the ECI frame with the corresponding orientation of the Earth fixed frame. So at that time, whatever the orientation of the Earth fixed frame, we assume that the ECI is aligned with that. Okay, then as time progresses, the Earth fixed frame continues to rotate with the Earth, but the ECI frame does not. Okay, it does not rotate with the Earth. So this is convention 1. So at different times, depending on when you are starting to navigate, the orientation will change. But as you fix the orientation, it remains fixed for the entire duration of navigation. So this is convention 1. The second convention is as follows. So we know that the equatorial plane of the Earth makes an angle with the orbital plane of the Earth around the Sun, right? And depending on distance between the Earth and Sun, as it moves in its orbit, we experience different seasons. Now, there are times in a year, in fact, twice in a year, we have equal day and night, right? When both the hemispheres of the Earth are equidistant from the Sun. So these times are called equinoxes. So at the time of an equinox, the Sun center is on the equatorial plane, and that's why the length of day and night is the same. There are two equinoxes in a year. spring equinox and autumn equinox. The spring equinox in the northern hemisphere is also called vernal equinox. Okay. Now the x-axis of the ECI frame is taken as the direction from the earth center to the sun center at vernal equinox, which is spring equinox in the northern hemisphere. So this is considered the x-axis. Then the z-axis would be along the earth spin axis at that time at vernal equinox, and then y-axis has to be on the equatorial plane, making a right-handed orthogonal coordinate. But this is also not precise. To have a precise realization of the frame, we need to precisely define the z-axis also, right? Because the earth spin axis makes a motion with respect to the solid earth, which is called polar motion. Okay, so it makes a circular motion of about radius 15 meters, and for a precise realization of the frame, we need to properly define the north pole. Okay. Now, for this purpose, IERS adopted a convention. It's called IERS reference pole. It is the average position of the pole surveyed between 1900 and 1905. That average position of the pole is called IRP, IERS reference pole. So the z-axis is along the IERS reference pole. You may ask, what is the guarantee that these two axes will be orthogonal, right? So what we do is, first we define the x-axis as the direction from the earth to sun at vernal equinox. Then the z-axis will be along the instantaneous north pole at vernal equinox. Then it is possible to go from one coordinate frame to another coordinate frame by applying rotations. You have probably heard of Euler rotation. In case you have not, don't worry about it. We'll talk about it when we discuss attitude. Okay, so we can apply suitable rotations to go from that z-axis to this z-axis, which is along the IERS reference pole or IR. Okay, so we start with this x-axis and then we apply suitable rotations to go to this z-axis, and that is how we define the frame. The ECI frame, whose origin is at the center of the ellipsoid, z-axis is along the IERS reference pole or IRP, and the x-axis is based on the direction from earth to sun at vernal equinox. This ECI frame is called conventional inertial reference frame, CIRF. Okay. So you will find the discussion of coordinate frames in chapter 2 of Paul Grove's book, and chapter 1 will be about chapter 1 is about the introduction, okay, where you will find all the derivation techniques. May not be the way we discuss in the class, for that you need to refer to the lecture material, but you will find discussions of different navigation techniques starting with the coming in chapter 1 of Paul Grove's book. Okay, and in chapter 2 we will find the discussion. So basically we are now following chapter 2, not the same way, but I will discuss few important things from chapter 2 for foundation. Okay, so this is how the earth-centered frame, inertial frame, is defined. Any question? Okay, so tomorrow we'll first complete navigation coordinate frames, and then we'll start representation of earth surface, the earth surface models, and we'll also discuss some associated parameters and terminologies in that context. We have 2 classes tomorrow. In case we complete the discussion, we'll have a short tutorial where I want you to explain the homework problems that I gave you last week. I gave you, I think, 2 to 3 homework problems, 2 problems on angular positioning and 1 on Doppler. Please look at them, and if we have some time at the end, we will have a quick tutorial tomorrow. But our objective would be to mainly complete the navigation coordinate frames and Earth surface model. In case we cannot manage time for tutorial tomorrow, I think tomorrow I will give you some more homework problems. We will discuss all the homework problems next Friday. Not this Friday, next Friday. Okay? And you have a test on 4th February. 26th is a holiday. Next Wednesday is a holiday. So tomorrow I want to finish art surface model so that next Thursday we can start attaching. Okay? That's all for today. We'll meet tomorrow again.
Thank you, ma'am.
Thank you, ma'am.